Okay, so I have corresponded in the comments talking about this. It's wrong. Question mark says it's wrong. Wonders what the hell I'm talking about. And first of all, I will respond to this. For one, the wave went through both slits. You would detect it behind both slits. The whole point of the particles being quantum is that you can't split them up and send them on different directions. The particle does not go through both slits. This is true. Yeah, a particle is just one thing, like a bullet. It didn't go through both slits. Why would the electron? The electromagnetic field, however, does. Because Einstein won a Nobel Prize figuring it out. The argument for the forward here was before the experts in the field you're arguing from. Like, seriously though, I'm gonna have to respond to this video directly. Besides the fact that I've already said, thank you for your reply, I will make a direct reply on this topic, this is that. And to summarize, the electron is not a wave, but the electromagnetic field, guides the particle. I can write, which goes through the field, even if you put a laser beam, another EM field interference is just another EM field interference which blocks the EM field. Yeah, so the laser beam is basically another electromagnetic disturbance which then blocks the wave from making an interference pattern in the first place. Veritasium made a video talking about how the electricity is sent not by electrons, but by the field also. If the electron was just a wave, it would have dissipated along with the waviness. So here's the thing. Observer is incorrect terminology, and the electromagnetic and stuff, and all that stuff. However, another thing to notice is that the electrons move at crazy speeds. That speed is like 2.2 quadrillion atomic width per second. Fun fact, quantum means it's not a wave? No. You realize quantum is just the size of it. It's like, instead of microscopic, it's quantumscopic or something. The reason quantum mechanics was invented in the first place is because stuff comes in quanta, like small packets. The thing is, there are still waves on the atomic and quantum scale. It's just, I'm not getting, God damn it, do I have to get into that too? Parts of the description of the behavior of wind is using the same mechanics and expressions of waves. It doesn't mean that it's the same thing described as a wave. Yeah, it's a bunch of particles that altogether behave like a wave. Just like how the electromagnetic field is a bunch of tiny electromagnetic subatomic components that interact and move like a liquid and a field. Let's get into the video before it starts even more stupid.
This tiny dude is a proton. Is it a particle or is it a wave? You have
Not a question. A proton is not even a thing. It is a collection of things. It is the film that is apparently around the atom, as well as the quarks themselves. moving around and jumbling inside of there, making the positive component. However,
Probably heard this debate about a gazillion times. Well, it turns out
I have never heard this at all. Not one freaking person in my entire time on the internet has talked about a proton as a wave. Photons? Did you say photon or proton? Fuck me.
this tiny dude is a proton. Is it?
Okay, you're talking about protons, part of an atom, as in proton, neutron, electron, not a photon, which has a pH, and not an R. A photon is wavy, not a proton, because, you know, light works in wave intervals and stuff.
The particle, or is it a wave? You have probably heard this debate about.
So, I'm sorry, from the very first nanosecond of your video, you have stated a false, not just a false statement, but complete misinformation that no one has in any, even the bad ones don't say this, okay? That's how far off you are. You've gone from, I'm going to make a good animated thing, and then you just, I'm sorry, you made a mistake. I'm harping on it. It is kind of a typo or a misread or a mishear, because proton and photon are similar in vernacular, but they're not at all the same. Everyone knows photons are light, and protons are the atomic particles. So, let's get that out of the way and move on to the next bit.
A gazillion times.
Never.
Well, it turns out almost everything you have been told about particles is kind of a BS. So let's see what is really going on. Are the protons best friends? The electron and the neutron. They love hanging out together. Toss in a few more and you have just built an atom. But wait a second.
No. Again, you're mistaken, because you start with a proton and an electron. That's a hydrogen, dude. You already have an atom. We can go smaller. An anti-neutrino, an anti-electron and an anti-proton was the first, like, antimatter. And it's technically smaller than hydrogen, which is fun. But technically, and it's unstable and whatever. Who cares? The point is, you don't need to add more to make, and you don't need to add this many. Also, I have so many problems with this. The number of protons and the number of electrons are not equivalent in this manner all the time or whatever, but that's irrelevant. So, is it a valid position and stuff? Kind of. It's an animation. Let's pass on that.
We may have a problem, because protons and electrons have opposite charges, and so they should attract each other, right? Kind of like you attract ridiculously complicated science. But
okay, protons and electrons are... First off, the electron is moving crazy fast, so it's also... We'll get to that. Let's...
if they attract, why don't they just collide and explode?
They do. That's called radiation.
Some random genius was like, yo, what if electrons orbit the protons, just like Earth orbits the Sun? Brilliant idea. Except it's actually a terrible idea. Because when an electron moves in circles, it emits light, and that uses up some of its energy. So an orbiting electron would lose...
Okay, that's a falsehood right there. Electrons do not emit light just because they are circling. They emit light when they change the orbital radius, because the more energy that's in the electron to work with, then it literally has to, first of all, it goes faster, and I'll get to that. Oh my god, Alright, so let's begin. Electrons move at a 2.2 thousand kilometers per second. What is that in relation to the size of an atom? Well, if you consider an atom to be 1/10 of a nanometer, really tiny, then it moves 22 quadrillion atomic whips per second. Now imagine a string that was 22 atomic whips per second long, going about 2.2 kilometers that way, and you try to roll that around an atom.
And then fall into the proton anyway. Congratulations, we have just solved, well, nothing at all. And this is exactly when the science bros realized that they were missing the bigger picture. Because it turns out that particles are not tiny solid balls. They are something way more bizarre. But what exactly? That was when this guy appeared. They called him Schrödinger. He showed up with one equation to rule them all, quantum particles. Okay, that's too many weird symbols for my taste, so let's do it other way. Imagine a tiny solid ball, but this time spread it across space. Now you have a tiny little cloud. Yeah, that's right. A particle is...
Okay, so again, like I said, if you take 22 quadrillion tiny little things, stretch it out like 2.2 kilometers, then coil that bad boy back up. And to illustrate this, I have a measuring tape. Now, let's say that you have about 16 something in here. And then for every millimeter that you have rolled up around this, you consider that an electron. Well, there's a lot in all of this. So that's why when you curl it up like that, that major distance that it goes per second, you end up with it going around an atom about 5 quadrillion times. So that's why it looks like a blur. There's a ton of them. It has traveled so many times that its past echoes still exist and influence itself. So it has to move over to the side a little bit in order to avoid itself and keep moving. And they're all also moving at the same speed. So it's like, hey, I'm looking at my past self, my future self, and another one from the past who's gone for like another bunch of trillions of a second, and they're all next to me. Yeah, that's why it looks like a blur.
Never really at one place. It isn't just here or here. It is sort of everywhere.
Yes, that's because it has literally been in all those positions in 1 second, because it goes so damn wicked fast. And unless you are as accurate as, I don't know, 1 quadrillionth of a second accuracy, or 10 quadrillion of a second accuracy, you're not going to fully see how many electron echoes are around the atom.
Basically, the gods said, let's play dice with the universe, and made their existence uncertain.
No, it's because the electron's influence over the electromagnetic field is what makes it go zoomy. And so when you take a zoomy and you put it into the positive effect of the proton, you end up with an orbit. And it can't go any closer because as electrons go faster, they excite the electromagnetic field and make the electro and magnetic field, and they literally push away with their negativity, which is not exactly negative, it's a negative positive, because electrons are a dipole, just like any other magnet, just really tiny. So the electromagnetic field is around and excited around the electron, and because of its speed, it has a certain amount of energy that it exerts. And when you add that extra photon to the electron, then you end up having it jump up because it goes an extra bit faster. that extra bit faster makes it go that extra bit longer a distance per second. And if you coil that up again, all of that extra distance means it has to take up a bigger mass of space. It literally is forced into that larger area, exactly equivalent to the amount of energy put into it, the photon. Now, photons of light go 150 times faster than electrons, approximately. It's more like 135 times the speed of an electron from when I actually did math in the previous video. Fun. But the main thing is that that amount of massive burst of energy gives it the extra amount of speed, which makes it have that many amount of rotations around the atom more, and so it literally cannot take up a smaller space, it has to take up a bigger space. And so when that photon finally is like, I'm out of here, then the electron relaxes and goes down to its normal energy state.
Bright spot? Yeah, existence is likely. Dark spot? No, nothing to find here. But this uncertainty isn't just some mathematical trick. It's not only that we don't know where the particle is. The particle is...
We're not looking. I don't know anyone who has looked at, like, when we talk about femtoseconds, we're starting to properly image an electron. I got a picture for you. You're gonna love this. Okay, so this is a picture I ripped off the internet of how electrons look when they're around things. It has a certain amount of, all these little dots that are around there. Well, every one of those dots is approximately the echo of the electron. That's one electron. All of this is one electron. Because it moves so fast, it literally bunches up on itself. And this is a cross-section of the total orbit, which is spherical in nature. Which is why you also see that sometimes, it'll orbit more circular, and then you end up with these patterns. Or it'll orbit more directly circular, so you end up with just the top and bottom. Because that's a cross-section. The total is a ring. This is what it looks like from one side. And this is what it looks like from the other side. Wow! It's changing direction as it orbits. Moving on.
Mathematical trick. It's not only that we don't know where the particle is. The particle itself doesn't know that either. That's what particle really is. It's just the cloud of uncertainty.
Now,
in our world, we can predict how something moves.
So, here's the thing about uncertainty and the cloud and it not being an orbit thing phenomenon. Ideas. Is that if you're going around an atom, there's no reason for you to stop moving in the most straight line as you can. Literally, something in motion wants to stay in motion unless affected by something else. So, knowing that, the only thing that's keeping it here is the pull of the proton and its own velocity and the electromagnetic field that it generates. If it had less electromagnetic field, for example, somehow, because, I don't know, someone heard it. If somehow it was emitting less electromagnetic field, then it wouldn't have as much of a velocity, because its influence over the electromagnetic field is part of what makes its velocity, as well as what makes the EM field bubble that's around it. Once you go faster with electrons, the EM field bubble increases. We see that when we put more energy into an electromagnet and it suddenly is able to pick up a car, whereas before it wasn't.
Exactly. Easy. But in quantum world, we instead predict how the cloud of uncertainty moves. And stop. After 1 second, the cloud got exactly here. Completely predictable. Now, let's make it more interesting. This time, we will smash the electron.
Now here's the thing, right? So if you shoot the electron simply at a wall, then you get a simple dot. Really simple, easy to notice. You don't even have to have a lot of education to get this right. And then you put a slit through a wall between it. How big is this? Does he say? I'm not going to tell you, but does he?
Thrown at the wall with a tiny door.
Yeah, very tiny.
Looks weird, right? It's because electron moves like a wave. And
Wrong. The electron doesn't move like a wave, but the electromagnetic field does. So everyone knows that the electromagnetic field is what is manipulated by the electron. It's going through it, it's going around it, it's the thing that connects it to the proton, and so we know that there's this other energy-based thing, works like a fluid, and knowing that, there's no way that we would ever say that the electron and this wave are the same thing. But everyone does it. I don't blame you for doing this. Everyone does this mistake. It is a mistake.
And this is what waves do. If you don't believe me, just look at these ocean waves. As
Yeah,
they hit
this is what happens with fluids. That's the electromagnetic field. Now here's the thing, right? This is just a single gap. So you get only one bubble. So when you have the two slits, you get two bubbles, they make the interference pattern. Which means that you'd have to have something that is already moving through on both sides. And that is the electromagnetic field. Not the electron itself. The electron is a tiny little dot moving with the field.
this gap, they start spreading in circles.
Yeah.
Now, let's smash that small cloudy bastard again, but at a single proton.
Okay. What?
That's some crazy shit, right? Okay, one last experiment, but this time, forget the violence.
First of all, when was that ever done? And second of all, what?
And just put the electron gently near the proton. It will not fall in, it just wiggles around. Give it a little more time and the electron will settle into a stable shape, like this, or this.
Depending on what side you're looking at.
You may know them as atomic orbitals.
Yeah!
So somehow,
And that's the picture I just showed you. Only you also get to see all the little tiny dots, which are where the electron is. Relative to... They've got to be going nanoseconds. They're not super accurate with it. And also, they're, again, just a cross-section.
when electron behaves like a wave, it becomes stable. It does not fall into the proton. But why exactly? Don't waves just travel endlessly?
I can't reconcile and understand what the hell you are trying to illustrate when you're talking about an electron being shot with velocity towards a proton. What are you? Where is this? Where is this studied? I've never heard that. Really.
So how come that the electron's cloud is just chilling there? Well, imagine a vibrating guitar string. It's a wave that is trapped between two fixed points, the ends of...
Yeah, and that's also considering the idea of a substance that is of said length and whatever, and those constituent parts are all moving because of their own elastic properties and such.
the string.
Tension?
It vibrates in place, but does not travel anywhere, because it physically can't. Now, just apply the same idea to the electron. Its
You try doing that, and you realize that the electron is just one thing, and the string is a string of many things. In fact, I don't want to... I can't tell you just how many, like, trillions of things are in any given hair on your head, much less a guitar string, which is thicker than a hair.
Cloud of uncertainty is held in place not physically, but by the proton's electromagnetic pull. It
Got that
creates
right.
sort of an invisible wall. The electron can't escape, but cannot fall in either. It may be a little bit more abstract, but it uses the same wave logic, so the end result is the same. So
I'm like Jax leaning over the sink, having a... But I'm just... Okay, let's back up. The electron stabilizes because its motion around the photon has been able to not be influenced in any direction, sideways or whatever, such that it becomes, circular, like any other orbiting body. Whereas if you simply have, let's say that you've tried throwing something at a planet, and it somehow reduces its velocity such that it's able to orbit the planet. But let's say, of course, it has some kind of autopropellant, which an electron does. It moves the electromagnetic field, so it's an autopropellant thing. It's free real estate. Actually, perpetual motion. In play, all the time, you're made of perpetual motion. Did you know that? No one says it. Fun.
well, now you may be thinking, okay, great, particles are waves, end of story. Except that's just the beginning, because quantum waves are not just casual waves, like the ocean waves. The equation
Well, I mean, duh. That's a collection of molecules that are behaving in a three-dimensional structure based off the total motion of some things and gravitational constant, air resistance, and all that.
equations that describe them are somewhat similar, but not the same. Plus quantum waves love messing with anyone who tries to look at them.
I'm sorry that it was a different size. It doesn't make much of a difference. They're not missing a lot top and bottom.
And this is where most quantum confusion comes from.
No.
Imagine an electron minding its own quantum business. Then suddenly it touches something big, non-quantum, like a detector, or even just a grain of sand. And that's exactly when everything changes. The wave kind of collapses, and suddenly we just see one thing at one.
Okay, so here's the thing. When you're shooting an electron, you still only see one thing. When it hits something, the reason why you only see one thing, it's the only thing interacting at that moment. All of this stuff happening at quadrillion times per second has reduced to a single instance of something happening in one moment. The end of its journey. So yeah, you get one thing because there was only one to begin with.
Place. Just like your will collapses whenever you want to subscribe to a decent YouTube channel. So basically we can never see the wave itself, only
No
a
comment.
collapsed leftover, which we usually call a particle. And this happens every time you look, no exceptions. So what
Yeah.
in the quantum hell is going on? Well, obviously another.
I mean, nice freeze frame. Look. Again, when you reference the speed of an electron, 2.2 thousand kilometers per second, recognize that 1,000 meters is a kilometer, and 1,000 kilometers is just a million meters. So you would just say 2.2 million meters per second. Or, referencing this area of the atom, if it's a tenth of a nanometer, like I said, then it goes to 22 quadrillion atomic width per second. Thinking about 22 quadrillion of anything is just going to blow your mind. But, yeah, that's why we end up with a blur, and that's why that one thing ends up collapsing to just one thing, because it always was one thing. It was just moving really fast in a tiny space.
A genius appeared and said, "Oh guys, look! Electron is both a wave and a particle."
No! The electron's always a particle. It's the electromagnetic field that makes the interference pattern we see in the double slit experiment.
It's a particle when we are looking and a wave when we are not looking.
You know also when you're interfering with an electron, looking at it with an electromagnetic beam like a laser, and you end up with like the shadow of it on the other side, which is basically how we do electromagnetic imaging. That kind of stuff is limited, and you'll only get the cross-section of things because that's how visualization works. The other thing is that when you're putting an electromagnetic field around an electron, then its influence over the field dissipates, and if you only have the electron to look at, then yeah, you're basically pinning it in place, so there's nothing else that is its weird motion and cloudiness.
Oh, the wave-particle duality concept. You may have heard of that, except it is kind of a nonsense, because the particle aspect is just an illusion. The actual problem is that we are
No, the wavy part is the illusion, the particle part is the only thing that is real, and for just trying to move away from that is like saying, if I throw a ball extremely fast, it stops being a ball, it starts being a wave. Yeah, the force of all of its parts will collapse on itself, sort of, and smush. And if you're going not too fast, eventually when it hits something, yeah, it'll bounce back into a ball shape. That's because it's a constituent of many parts that have elastic properties. Electron, however, is extremely tiny in particle, but it also makes you think, what is the electron really made of? Because it's actually made of extremely, even more tiny constituent parts. That's the same type of thing as, what is the proton made? Quarks and stuff.
With something so tiny that just trying to look at it messes it up completely. And so when we want to look at a quantum wave, it changes from being spread out to being super localized. But it's still a quantum wave. It's just that its cloud of possibility shrinks down. That's all there is to it. And
No, it's more like you're actually looking at the thing in one of its instances of time. If I were to simply take a visual, imagine you have a roundabout and you have cars moving at a regular speed, let's say 40 or 30 kilometers an hour. Not too fast, because roundabouts, right? You can't go too fast around them. But you speed up that image of them going around, even if it's just one car, eventually it'll just look like a blur. But when you slow the footage down, it's just one car, and you see that. So when you get more accurate measurements, like to the quadrillionth of a second, yeah, you'll see a particle. Because you're now looking at just one car. Not all this after image persistence of vision glitchy type of behavior, which is just, again, persistence of vision. Woo! How many fingers do I have? It's still 5, even though you don't see them. You get it?
Collapse, the quantum wave continues traveling just like a wave. So what
Do I have
looked
2
like a
fingers or
particle
1 up?
was just a
Just
quantum
1!
wave pretending to be a particle.
No,
One question remains though.
the electromagnetic field does that waviness, not the particle.
Why the wave even collapses? Yeah, nobody really knows, but we do know one thing for sure. It's not just about us looking. It's about the boundary between tiny quantum world and our big world. At some point, this...
No, not really. The thing is, in order to look at anything tiny, you need to be using something like, I don't know, photons, which are an order of magnitude smaller than an electron. And their ability to be nearby an electron is so limited because of how they interact with each other. So if you were to say, change the frequency of the photon laser beam, you can go even smaller and faster and visualize the electron really cleanly, because any discrepancy between the frequencies is also part of the image of the electron. Oh wait, we're already doing that.
two worlds have to align to one consistent thing. And that's where weird things happen. Alright, now that you've got some quantum muscle, let's solve the most misunderstood experiment of quantum physics, the double-slit experiment. It's the experiment that shows that the electrons are sometimes waves and sometimes particles, depending on what you do. So what's the truth? The experiment is pretty simple. We take a single electron and smash it against 2 tiny doors. That's it. So what is going to happen?
This is not what we do. We aim for in between one of the doors. It can't, if the electron were to simply hit the area between the 2 doors, you'd see nothing on the other side except for the electromagnetic field. What we're actually doing is we're shooting it through one of the 2 slits. After that, the electromagnetic field making the 2 crests, as it goes through, it starts as 1 crest. It makes 2 crests. Those crests make an interference pattern that looks like that, spreading out, where there is, at its thickest point are the waves making pressure, and at its thinnest point are where the waves are making less pressure. So you're being pushed on either side, really. And so you can only go into these channels in the interference pattern, which is why you get that on the backboard, which is where the electron actually ends up.
Now that you know that the electron is a quantum wave, it makes complete sense. The electron's cloud goes through both of these 2 doors. At each door, a new wave is formed. Then these 2 waves interfere.
Yes.
Just like water waves would. This new...
Not the electron, the electromagnetic field. The particle itself is guided by the like I said, the spreading out.
Funky wave continues traveling until it reaches the detection plate. Since that is a big non-quantum thing, the wave collapses randomly at one of the bright spots. Do this a million times.
Yeah, here's the thing. Aha! You end up seeing it happening randomly, is where the electrons end up going. And they always end up in dots. So why is that? It's because they are dots, going through the double slit, being interfered by with the interference pattern, as well as due to their subatomic, like the electron size differences. Not to mention, you know, the double slit itself is made out of atoms which have protons and electrons in them? Wow! It's actually polarized, meaning all the different quantum fluctuations that are happening on the double slit walls themselves are what makes it choose which of the different interference pattern wave empty zones it's going to end up going into. And from then on, it really can't switch which of those channels it's in, because there's high pressure on one side, high pressure on the other side. It has to go on one of these parts. But which part can be determined. And if you take a record of all the different dot positions, you would be able to know if you have very accurate timing of when they landed. You can track back to where they would have ended up and what kind of bounce it would have taken for them to end up in that channel.
Recording where each electron lands, and you will see the famous interference pattern. This was really done by the science bros, and it proves that
it's actually the anti-interference pattern, the empty spots. The true interference pattern is the high pressure spots, which are where the waves are interacting constructively. All the electrons are in where they're interacting destructively, where the pressure is the least amount. Same kind of technology can be used to make sound levitate a droplet of water, because all that pressure on all sides is what makes that drop of water stay in place. It's being pressured by all sides. Similarly, the electron is being pushed on both sides. Amazing what would happen if you put the double slit instead of slits. You make 4 dots, so it's a 3-dimensional representation of the interference pattern, and you'd end up with the same 3-dimensional representation of the interference pattern is where they would end up. The places where all the pressure is the least.
Electrons indeed behave like waves.
No.
Now here's the twist. We add a detector to one of the slits. You may have heard that this forces the electron to act like a particle, because in this case, the
electromagnetic field is now being interacted with by an electromagnetic beam, forcing its electromagnetic waviness to just be completely cut off. Its momentum is shot to hell. So you can't no longer interfere and spread out. It's like cutting off your fingers. After this point, they no longer keep on going in those directions. And the closer to the double slits you make this beam, the less of the interference pattern is there before the spreading, and therefore you end up with it acting like a particle, because the waves were interfered with by a gigantic beam. Compared to an electron, a laser beam is really huge, and it's just in the way of the electromagnetic field. Can't get through it. You'd have to have a much more powerful wave, or a much less powerful laser. Less powerful laser, or pulsing micro laser. You're not using that. Bad experiment.
pattern disappears. But guess what? We can still explain what happens using only quantum waves. No need for particles. So let's place another detector behind the doors. In this case, if we repeat the experiment 1,000,000 times, we will just see 2 spots. It looks like the electron is now behaving like a particle, not a wave.
That's because it was never the electron choosing its path. The electromagnetic field was doing that. And it is not a standard camera. We're talking about an electromagnetic beam known as a laser shooting across, again, chopping off the waviness. And yeah, you only end up with the two. That's just how it is. Yeah.
But let's have a closer look. When we measure the electron as it passes through, it will collapse the wave. So now there is no second wave to interfere with, which means that the wave just continues to travel on its own. And when it finally arrives at the detection plate, it will again collapse at a random bright spot. But this time there is no interference because there was no second wave. So this experiment doesn't prove that the electron suddenly started acting like a...
There was no interference because, again, you cut it off so close to the double slit that the interference pattern of the electromagnetic field wasn't able to propagate out. It was immediately cut off. It's like if you ever go to the beach and you try to make a wave towards another wave, you can stop it from getting to you. I do this all the time at wave pools. It's really fun. The thing is that all of the force of that other wave is dissipated by the wave of energy that is going across it. And if you understand that, you know exactly why. And again, if the electron was a wave, it would have also been dissipated. Not just the waviness, which is why I said that in the comments, but the wave and the particle would dissipate. If it's actually a wave and the fidelity of the laser is small enough to interfere with the electron, if it's a wave. But again, it's a particle. Physical thing.
Particle. It just means that the wave lost its chance to interfere with itself. So, believe it or not, everything can be explained using only quantum waves. We don't really need
Again, yeah, you can explain the quantum waves part. We're not saying that doesn't happen. It's just the thing it's happening to. It's not the electron, it's the field. It's like talking about the static electricity that's around a balloon. You don't think of it as the balloon, but it's the thing that binds the balloon to your sweater or your hair and makes your hair stand up. Fun fact, if you're out in the possible lightning storm and there's static electricity in your hair, get down, because that shit's gonna strike nearby. Because there's literally enough static electricity in the air. All the EM field of everything, including the most easily affected, your hair, is just going to stand up. That's crazy, right? Electrons aren't doing that. That's the waves of electromagnetic field interfering and doing crazy stuff, because that energy around the lightning bolt where it's about to strike is just, it's huge. Duh. So it's like, yeah, be careful around static energy like that in the wild. Duck and cover.
Not particles. So yeah, I hope that makes sense. And
It
also
doesn't.
Because if it all made perfect sense, I would have nothing to make videos about.
Yeah, unfortunately, because you didn't have the understanding of the electromagnetic field in any of this, you never talked about it, even though it's an understood, like, solid textbook thing. Yeah, of course you didn't understand this. You're regurgitating other people's garbage. And I'm sorry that you're experiencing this. I'm sorry that you don't know how the electromagnetic field works. And it's interesting to think, go one step further. It's not just electrons and protons, it's everything affecting the electromagnetic field. In other videos I talk about how that's part of long-range gravity. It's the electromagnetic field and its influence from like Jupiter and the Sun. That's their connection. A massive area of electromagnetic field that is just flowing between the both of them. It's so minute and tiny, but it's only how it works. And this is interesting. Gravity is said to be how masses affect each other, right? And they think it's about the warping of space-time or velocity. But again, if I'm going fast on my bike, I'm not warping space-time at all. I've talked about that a lot in other videos. Go check those out if you found them interesting. I'm sorry that the problem is, this is not just him having this mistake. It's NASA. It's everyone else out there. Gobbledygook, PBS Spacetime, freaking anyone. Desmond, Destin, Dustin, Desmond, Destin. Smarter every day. I'm not kidding. Everyone who talks about science talks about the electron as being like a cloud and a wave and stuff, and it's unpredictable and whatever else, except for very few videos which mention that electron is one, a dipole, like any magnet, and two, basic textbook stuff. An electron moves at 2.2 thousand kilometers per second. That speed, tiny space, you get these crazy effects. Anyone using their actual head about it will understand it. Anyone who's just looking at the textbooks and trying to make a video about it won't. I'm sorry. I'm talking to Neil deGrasse Tyson and telling him off every time I get a chance to, because he also mentions the double slit experiment. He's just as much as wrong as everyone else, and I'm sorry. We have to move past this. We have to go into analyzing the speed, put it into constraints. What would that actually do? And because we know it's just an electron, because we know the waviness is interacting, we know that's a separate thing. But just looking at an atom, you can tell the electron and the proton have this relationship, this connection to each other, made by the substance of electromagnetism. Which is crazy, right? But it's interesting to note that, okay, that explains one thing. Let's explain also, let's go back to that other picture. Can I press the button, please? You bitch. Thank you. Okay, so why, based on speed alone, all electrons would have to enter the same orbital area? But because a certain amount of protons can pull at a certain strength, the electromagnetic field interfering with itself, only a certain amount of electrons can fit in that area. So you end up with something like this, where they're orbiting and another set is orbiting here. So the interesting thing that's happening with all of this is the motion of it moving sideways. This is the motion of it being a band that's moving straight up and down. And this is the motion of it moving around the atom like that. The orbit is fluctuating because its total momentum is not a perfect straight on the plane field. It's off by a little degree. So it changes constantly. And that's a whole other picture. I would love to get a tattoo of this, to be honest. But like, it's crazy thinking about all of this. And this is what it looks like, because the actual picture is... It's one of those pictures that you're supposed to have, like, with another object behind it. So I didn't switch pictures. This is the same picture. But then instead of having white behind it, when you actually look at it, it only has this. So it's like, again, 2 electrons, 6 electrons moving up, one moving up, one moving down. It's actually the same electron moving up and down, because its orbit is able to flip on itself. Normally, like, you have, let's say, It's interesting that you have two electrons, but they're able to move in this way, where it seems like there's less there. You can't see it as contrastingly, but you see it as more crunched up when you look in the black format, because there's a lot more difference between total black and that and total, what is this, beige? Like there's that blurriness that makes it hard to see, but when you look at it with the darkness, it actually is more condensed and close together and everything, and more spread out, and that's more obvious. Just fun. I love this picture. Just imagining how every one of those is just one electron because it's going super, super, super fast. Again, quadrillion a second. Anyway, that's about it. I don't know what to tell you. Electrons are not waves, they are particles, they go in orbits, they're just super fast. And like my man with the Science Asylum, that's fast. That's how they work. And the sooner we get past that, the better. Now, here's the thing, right? Think about all this stuff, and if we were to say that electrons are waves and electrons are particles, then we would, again, be forgetting about the electromagnetic field, which is a whole separate thing. And you have to imagine, you're going like quadrillion orbits per second. You end up bumping into yourself, having to move over to the side in order to continue to move forward. Like, if you look at this over here, that's it orbiting from the side as it goes around. This is it orbiting like this, and this is it orbiting like this. That's why we end up with the different patterns we see, because it's changing its direction, because its direction isn't a straight up and down. It's also slightly skewed, constantly adjusting, constantly changing. That's why it's fluctuating all the time. But yeah, it is nutty, but persistence of vision stuff is not so much an illusion. It's literally like, and the reason I say echoes is because these electrons all exist in that same second. So the electromagnetic field and the energy that is manipulating everything, their own physical presence, is all there at the same time. People actually trying to use persistence of vision in anime are using the examples of what electrons do and trying to say, what if a person did that? It looks crazy because visually we see them, a copy of them here, 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 and here. And when you actually stop to bump any one of them, it collapses to just one of them. The truth is, they physically are occupying all of those spaces. They don't just stop and you bump. It doesn't matter which one of them you bump. You're going to bump the real one if you're correctly in line with them every trillionth of a nanosecond of a second. Every trillionth of a second, if you're able to be there. Otherwise, because they're moving so fast, they literally jump out of the way as you're moving towards them. You moving towards them is like a really slow guy running towards them, and they're able to just not be there because they're going so fast. That's how persistence of vision works. They're going faster than visual can recognize, and they're only stopping to make the image of themselves. There is this stupid idea of the shadow of the actual one would only exist where he actually is, because that's what they think of when they think of the persistence of vision thing. With an actual electron, the shadows are everywhere. Also, you can't tell. And they all physically exist all in those places at the same time. Yeah, the shadow thing is a myth when it comes to anime. Look. The shadow of my fast-moving hand is also moving along with this thing. And the faster you go, persistence of vision, like, in order to make your shadow only appear on one thing, you have to be moving faster than the speed of light, and people in anime can do that. But we're not saying that's what happens with electrons. They're not moving faster than the speed of light. They're literally moving, light is moving 130 times faster. But it depends on, like, it's not so much moving faster than the speed of light, it's the idea of if you could see all the light that's going around you, technically, you could dodge all of the light particles and become invisible if you're moving fast enough. Superman can become invisible. Let that sink into your head. But it's an anime. Superman's an anime. I will not have this debate. Anyway, yeah, the other thing, like, I mentioned all sorts of stuff from how relativity is completely false, time dilation is a myth, people are misunderstanding what actually happens in time dilation experiments. It's more of a moving target situation, and I'm not going to keep talking about it. My phone's going to die. So anyway, go check out the other videos to find all the other stuff. This is the most I can give you of an explanation of electrons and how persistence of vision works, how the speed of them works, the waviness is from the electromagnetic field, not the electron. And when you understand that, you're able to actually do experiments based on that. But you're a scientific communicator, and it doesn't really make any difference to you. But just saying, this is how it actually is. I'm sorry. This also means that time machines and the idea of warping space-time to make the Kubier drive will never happen. And if you ever go as fast as the speed of light, you're going to disintegrate. Pretty sure. Technically, we haven't moved things faster than the speed of light in a vacuum. We haven't, like, tried to move a ball faster than the speed of light in a vacuum. Here's the thing. Neutrons don't like to be moved by magnets. They don't. So the only thing moving the neutron in a stuff that is moving fast is the strong and weak nuclear forces that hold the atoms together. Once you start going so fast that the neutrons can't really and don't usually keep up, and they just, like, eject themselves because they're left behind as the rest of the matter is moving much faster. Yeah, it's not good. All the stuff just decides to disintegrate. It's not a fun thing to happen. Yeah.